Okay, I don't know. Maybe we should start. So this is
Yeah,
the
okay.
this is the final meeting of the seminar this semester. So yeah, it's yeah, I'm sorry it's on the Zoom. Yeah, but I on the
Yeah,
other hand,
that's okay.
I'm very happy that we have Tianqing will finally get a chance to speak in the seminar. This, so we'll learn about all the great things he's been doing. Please.
Yeah, and very much thanks for this invitation. And today, actually, I'm going to talk about the quantum difference equation from shuffle algebra. It's will only focus on the case of the finite quiver varieties. And this is based on the work in the last year, and the work actually is going to be on the archive during the dinner. So, yeah, we're going to start with yeah. I posted last week, but it turns out that it should be on the archive today. Yeah,
Okay. So this is
yeah.
yeah. Of course, everybody will
It's so
just
gonna.
drop whatever they're doing and just start reading. Yeah.
Yeah,
Okay.
yeah. So since the seminar will last about 2 hours, and I think I'm going to tell something maybe in detail. So let me first start with geometric things that we consider. And the geometric thing is actually the affine type A quiver varieties. So let me first give a introduction to what is the affine type A quiver variety. So maybe the best shortcut is first I wrote down a graph, a quiver, which is consists of some vertex and arrows with a direction. Mm, yeah. So this is I shall take this one, for example, like V1, V2, V3, and then Vn minus one, Vn. And these circles are actually they're usually named as the gauge knots. And I tell the meaning of these numbers and this and the shape of these knots later. And each of these has some like this kind of framing. These are called the framing knots or the framing vertex. So the meaning of this quiver means the framing. So each of these knots stands for the stands for some of the vector space. So for example, if the nodes are so if the vertex such as V1, it stands for this V1 is just actually a number. It's like a number. So I denote all of this number in the vector. So this number is actually the positive or non-negative integers. And each of the numbers stands for the dimension of the vector space that this vertex corresponds to. And each of the arrows stands for the morphism from one vector space to another. So for example, if I take this one as x1, y1, x2, y2, and this one like x and yn, and xn minus one, yn minus one, and this one like a1, b1. So the meaning of this morphism is the following. So this x1, you can see that it is a morphism from v1 to v2, which means that actually, for example, this v1, it is just like a morphism from vector space v1 to vector space v2. And this y1 stands for a morphism from v2 to v1. And so you can follow this procedure. So this a1, b1 that stands for the morphism from v1 to w1. And usually we will pick up all of these morphisms into a vector space, which is actually called the quiver representation space. Because all of the quiver that we consider here are actually the affine type A. So this Q it doesn't matter too much. So if we write down this morphism into a package, so it should be look like the following. So you can see this morphism space stands for, so this morphism from Vi to Vi plus 1 just stands for, we can write down the elements in here like Xi stands for the morphism from Vi, for example, V1 to V2, and Vi plus 1 to Vi, we can just write it as Yi. And morphism from, for example, like Vi to Wi, we can write it as Ai, and etc. This Bi, which is the morphism from here to here. Yeah. So these are the basic things that we consider in constructing the quiver varieties. And on this space, there are actually two Lie group actions. Actually, it's three, but I'll first introduce the first two. Yeah, the first is given by the automorphism of each of the vectors of the Gaussian vector space Gi, which is written in the following way. And second one is given by the automorphism of each of the framing vertex, which is given by this. And you can see that we can construct, and the action of this GV acting on the representation space is actually Hamiltonian, which means that we can write down a moment map with respect to this group action. And this moment map can be written in the following way. It can be written as, for example, like Xi, Yi. Sorry, yeah, Yi. Sorry, it's like the following: Xi minus X Y, then plus BI AI. Yeah. So this is the moment map from the representation space to the dual algebra of the Lie group GB. And using this, and actually we fix a stability condition here. And throughout this paper, throughout that, I will assume that the stability condition to be like all to be of the positive ones. We can define the quiver variety as we consider as the theta some stable points, which is actually the theta stable points over here. So this is the definition of the affine type A quiver varieties. Yeah, and actually the main object here we're going to study today is the main object we're going to study today is the equivariant K-theory. Of this quiver variety. Yeah, and this TW is, I'm going to introduce it later, this TW consists of these two torus, is AW times C cross Q times C cross T. Oh, sorry, C star Q and C star T. And this AW is the maximal torus inside of the framing of the automorphism of the frame group. Yeah, and this C C star T and C star T, it acts on the quiver variety in the following way. So it's gonna act on quiver variety as the following. Yeah. Yeah. And this AW is just acts on the repetition space, just acts on the quiver variety in the way as it acts on the vector space of the framing nodes of the framing vertex. Yeah. So the main object today is the equivalent K-theory with respect to this group action acting on the quiver varieties. And actually, what we're going to study is actually an easier version, is the localized version of the equivalent K-theory. And the algebraic things we're going to study today is the quantum toroidal algebra. Yeah. And this n is equal to, and this v, and this w. Yeah. Yeah, so we're gonna introduce this quantum toroidal algebra later, but first thing we're gonna give some introduction about the fixed point of this torus section acting on these quiver varieties. So we're gonna first start with the fixed point, like some brief introduction. So there are actually two kinds of the group actions. The first is by this maxima torus, and the second is given by this. I don't know how to call it, by this two-dimensional torus action. So for this first one, I shall take it as 1, and this is as 2. Yeah. So for the first one, the general procedure is the following, that we take a co-character of this torus such that this character will decompose this framing vector, this W, into the following subvectors. For example, if we take it as W1, W2, plus until WK, such that W1, the sum of all of these vectors are equal to W. In this way, we can, if we treat the action with respect to this co-character, in this case, the fixed point corresponding to this group action is isomorphic to the disjoint union of some smaller quiver varieties, which is written in this way, such that the sum of the framing vectors and the gauge vectors is equal to. So because I forgot the name of this v, so I just name it as of this v vector and the w vector as the following. The sum should be equal to the original ones. Yeah. So usually this group action is called the framing group action, the framing torus fixed point. And usually you can see that the fixed point with respect to this gauge group is actually not isolated. But we can have the isolated fixed point with respect to the second two-dimensional torus action. So the second one, it is much interesting that if you take the fixed point with respect to the group action in its form, you can see that the fixed point is equal to the W partition lambda, and this lambda is a set of partitions such that the sum of this partition I mean the box inside of this partition is equal to, is equal to the sum of this, the size of this vector, which is equal to W1 to W, and and with some constraint condition. Actually, I'm not gonna tell you about what is the constraint conditions, but I can give you one example, like how to do about these partitions in this case. What does it mean to say about the W partitions? So it means the following, like suppose that if my vector is like 2, 3, 3, then this W partition just means that I have a bunch of partitions of integers, which is denoted by lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, lambda 7, lambda 8. So this W so the notation here of this W, it just means the sum of each component of this vector. So the sum of this is like 8. So there are actually 8 partitions over here. And this is actually really good because in this case we can have the isolated fixed points. Yeah.
Do we also need the framing torus to get isolated fixed points?
Actually, no. The framing torus actually just decomposed into smaller pieces. Yeah. Yeah. So these are some basic things about the affine type quiver varieties. It means that actually, because actually the main thing is about the main thing that we're gonna mention is about this fixed point torus. Oh, sorry, about this fixed point, because after doing the localization, if we do the localization with respect to this torus section, this will be a this dot point vector space spanned by the fixed point basis. Lambda, yeah. Yeah, so this actually some geometric things that we need today. Yeah. So any questions so far?
I think Sam was correctly pointing out that you need both the framing torus and this torus to get isolated fixed points. Just one, this two-dimensional torus is not enough.
Oh, you mean oh yeah. Sorry about this. Yeah, I want to mention that. Yeah. Sorry. Yeah. I need to add this. Yeah. Yeah. So sorry about that. Yeah.
Is it easy to say how the fixed point translates into the x, y, a, b you write earlier?
And I introduce it later when I introduce the shuffle algebra. Yeah.
Oh, okay.
Yeah. Oh, which will be a little. I don't know. Which will be a little bit chaotic for me. Yeah. Yeah. And yeah. So our next page is So at first I want to introduce. I'll introduce some motivation for the quantum difference equation, but this is the algebraic ones. Yeah. So the motivation goes on the motivation comes from the theoretic capping operators. So let me briefly introduce what is the theoretic capping operators. And so the main object in geometry, the main motivation in geometry is that we study the quasimap, actually the stable quasimap from C, which is actually has the connected component as P1 to this quiver variety. Actually, the meaning of this quasimap from C to this quiver from the Lefant quiver varieties means that actually it is first mapped into the genetic quotient of the it's first mapped into the genetic quotient, and then most of the points from C goes into this stable points, which is actually from in the Lefant quiver varieties we mentioned before. Yeah. So we consider this kind of space. Like it's a space from here to here. And usually in here, we consider the following kind of the restriction. Like we require that this quasimap should be non-singular at P1. And with some relative at P2. And relative here, it means that it used to be non-singular, but we do some kind of the compactification to enlarge this quasimap space to make it more feasible for us. And yeah. So we consider this kind of the modular space of this stable quasimap from P1 to the quiver varieties. And this modular space is actually, each of these quasimap is actually graded by the pickup group of these quiver varieties, which in here, in our case, this is moving to Zn. Yeah. And yeah, and with respect to this two restriction that non-singular at P1 and relative at P2, we can have a violation map. One is at P1. Oh, sorry. Another is at P2. Map this quasimap space to the product of two quiver varieties. Actually note that this map is actually, this map is actually not proper, but the good thing is that it becomes proper. It is proper on the fixed point. Oh, sorry, I did mention the fixed point of which torus section. So in this case, this torus section is like the first torus section, this, and another torus section, CP star. Yeah. So this CP star is the torus section naturally induced by the automorphism of P1. So combining with this two torus section, this map is actually, so we can take the fixed point with respect to this torus section over this map. Yeah. And also on this quasimap space, we have the twisted virtual fundamental sheaf. So with this object, we can define the capping operators. In the following way. this OD means it is the virtual fundamental shift with respect to the component of D. So yeah. So you can see that this is an object in here. Yeah. And this ZD, it just means, so for example, if I take this D in the component way, so this ZD stands for Z1, D1 to Zn, Dn. Yeah. Yeah, and usually you can see that this U is actually the variable in the equivariant parameters. It belongs to here. So this is U, this is Z, and yeah, usually we can take this Z as the coordinates in the Picard torus. So this is like so usually we can take we call this U parameter as the equivariant parameters. And this Z as the Kähler parameters. Yeah, and a good thing about this capping operator is that, good news is that this capping operator it satisfies the following difference equation. So actually, because I'm only gonna start with the Kähler variable. On the Kähler variable ones, it satisfies the following difference equation. And here, this L is an element in the Picard group, in the integral Picard group. And this PL just stands for example, if I take, so this ZPL stands for the following. So if I represent this L as some integers, like K1 to Kn, then this ZPL means Z1 P K1 to Zn P Kn. Yeah. And also, actually, you can see that on the variable of U, on the U side, it still satisfies another set of the difference equation, which is actually on that side is actually more or less like the QKZ equation. So, but the main object that we're going to study today is on this equation. So here the thing is that if you want to know how to solve this difference equation, the first thing is that how to compute this MLZ. And this MLZ, I shall call it as the quantum difference operator. In the computation, yeah. So the main question is how to compute this quantum difference operator. The thing here is that, yeah. So the first proposal, in the geometric way, the construction is given by the Okounkov and Smirnov. So the construction it looks like the following. So maybe I should introduce. Yeah, so the construction is actually given the following way. So I sketched the construction of this. The construction is, so the first thing is that we need to have a quantum group. Need a quantum group. And this quantum group is given by it is actually the Malik-Okounkov quantum affine algebra. which is written is the following. Yeah. And this M quantum affine algebra, it is constructed by the stable envelope, the theoretic stable envelope. And this stable envelope, I can take it as SL from K theory of, for example, from M1 times M2 2. Here I need to explain what's the fish here. So this T, MW just means we take all of the gauge knots and sum them together in this way. And here this stable envelope, it means that we take it is a map from the K, it is a map from the equivalent K theory from one of the, so we take the fixed point action on this W such that this W can be decomposed as W1 times W1 plus W2. So you take this fixed point, and this is stable envelope that constructed from this fixed points equivalent K theory to the original ones. And this stable envelope, it is actually, sorry, this is like, so this is C. So this L is some parameter in the, yeah, I can take it just as here. It lies in the rational pickup group, and this C is the choice of the chamber corresponding to this torus section. Yeah. And using this stable envelope, you can construct the geometric R matrix, which is defined as here, the inverse of this to here. And I should say this, yeah. The basic thing about the stable envelope is that it is isomorphism after doing the localization. Yeah. And it is triangular, actually. It's triangular with respect to the fixed point components. And actually, there's an order on the fixed point components, but yeah, the order is given by the flow, by the direction of the flow. Yeah, for the attracting space. Yeah, so in this way, actually, could define this geometric R matrix. And this geometric R matrix is actually, if you do the computation, you can see that this geometric R matrix satisfies the Yang-Baxter equation. And using this, we could use the additive formalism to construct the M quantum affine algebra. Yeah. And the good thing about this M quantum affine algebra and its R matrix is that it satisfies a factorization. And this factorization is given by the following. So we know that this stable envelope has actually one other thing, is that this stable envelope is locally constant. It is locally constant on S plus 2. Maybe I should just write it as Qn. Yeah. It is locally constant on this variable S, and actually we should call it the slope variable. Yeah. Sorry, the slope parameter. And so the fact is that this stable envelope actually it will change its value if if S jump through some walls or the hyperplanes in Qn. So for example, if I have a stable envelope in here, on this point S, and I go across this wall, I take this wall as W, I go across this wall to some new place like S prime. In this case, actually the stable envelope will change. And in this case, we shall call this, and we can also define a null matrix when with respect to these two different slope parameters. It is defined as the following. Yeah, and you can see that this wall line matrix, it still satisfies a Yang-Baxter equation. Actually, it's not quite true, because we need to multiply with some kind of scaling operator to make sure it satisfies the Yang-Baxter equation. Yeah, but actually that's okay, yeah. But anyway, using this R matrix, we shall call it the wall R matrix. Yeah, still we use the RTT formalism. We can use this wall R matrix to construct an algebra, which is the wall subalgebra. And this is a subalgebra inside of this M quantifying algebra. Yeah, the good thing is that this geometric R matrix, it can be factorized with respect to this wall R matrix. Yeah. So the thing here is that this plus minus sign here, usually you can think about it as, so this minus sign, you can think about it as some matrix that is lower triangular. And this upper sign just stands for the matrix that is upper triangular. Yeah. So the understanding about this factorization from one point is that, actually it's just some digression that, so from one point is that this R matrix, this geometric R matrix actually has the matrix coefficients as the rational functions with respect to the equivariant parameter. And this factorization, you can think about it as doing some Lagrange expansion of each of these matrix coefficients with respect to something, with respect to a formal power series. So from this point of view, there should be like some kind of factorization. Yeah. But it's not should be, yeah. Yeah, anyway, yeah. So the key thing is on this wall subalgebra. Yeah, using this wall subalgebra, actually you can, yeah, this is the key thing. So for each of this wall subalgebra, and this corresponds to some of the wall inside of this slope parameter space, we can construct, which is called the wall conditioning homological equation, or it has another name which is called the ABRI equation, which is written in the following way. Yeah, maybe I don't want to explain too much about the sign, so I shall omit this operator here. Yeah. Which I think here. Of course, there should be something like the function, like the function over the z. Yeah. And so key thing here is we have this work is the equation, and here I need to explain the notation here. So this Tu is, because we know that all of this kind of thing has two variables. One is the Kähler variable. Another thing is about the equivariance variable, because we know that geometric R matrix is something with it is some matrix with the equivariant variable. So this means that this T is the translation operator, translate from U to U times P. Yeah, and this Z1 means the following. So we know that this equation, it actually acts on it. It is something really universal in the wall subalgebra. So actually, we can use this equation to act on some vector space, like V1 W1 times M V2 W2. Yeah. So this Z1, this notation just means it is the multiplication of the Kähler variables in V11 to Vn, sorry, V1n. Yeah. And we shall take this vector, this dimension vector as the, yeah. So good thing is that this equation has a unique solution. And we shall take this unique solution with respect to the wall subalgebra as JW plus Z. Yeah. And using this unique solution, we can define UW minus Z as the following. Yeah. Yeah, and this SW are the antipode of the wall subalgebra. And using this operator, we can define the monodromy operator. Or maybe now I just think that would happen here. It's defined as WZ. It is the product of both sides of this operator JW minus with the shift of the Kähler variables by a multiplication of this Q things. Yeah. And this C here is the Cartan matrix of the Van Tappe. Yeah, so this is something in just one wall subalgebra. Yeah. So the thing here is that fix a quiver variety like theta. We can choose a path, for example, like S, the point S still in the Qn, that pickup space, to S minus, to some like S, it's not so good to write in this way. Yeah. S to S minus L. We choose a path from S to S minus L, and this L is an element in, there is no pickup group. And we can see that on this path in the Kähler space, this path will intersect with finitely many of the walls on this path. So for each path, every time when this path goes through one wall, we'll take one of the monodromy operators with respect to this wall. So it means that we can define the following operator with the left multiplication given by S. And with the ordered product of the monodromy operators in the path. Yeah. So the good thing here is this is a theorem by Okounkov and Smirnov that if we take the difference operator, this TL is just the notation to define the shift of the Kähler variables. Yeah. So the theorem is that this quantum difference operator is actually conjugate to the operator defined above up to a constant. And then and the good thing is that this conjugate is given by the stable envelope of slope S. Yeah. And another thing is that this operator, they actually construct a holonomic system over the Picard-torus. Yeah. So this is a quite long. Yeah, this is a quite long sketch about what is the construction of this quantum difference operator. Yeah. So the key thing here is that the construction of the quantum difference operator depends on how you construct this monodromy operators, and using this monodromy operators to define this operator. And actually, I should still call it as the quantum difference operator. So one thing is about that. Yes. So I shall present some good news. The good news is that if this quiver, for example, because this construction can be constructed via arbitrary types of the quiver. So if I take this quiver as the finite ADE, then this MO quantum affine algebra is actually isomorphic to the quantum affine algebra of the corresponding type. In this case, you can see that this difference operator is actually equivalent to the construction given by Okounkov and Tianqing's construction. And this monodromy operator, it is actually the dynamical wheel group operators constructed in here in EV. Yeah, but that's the only good news, because for the other types of the quiver varieties, for the other types of the quiver, for example, like if we take the Q to be like the affine type A or the affine type ADE or some other types of quiver, actually we don't know how to, like, yeah, it's not that good that we don't know how to write down. We don't know whether if there's a isomorphism between the ML quantum affine algebra and the original ones. Yeah. The only thing we know that there's an embedding from the right hand side to the left hand side. So the main motivation here, so this is the main motivation, that we want to study the affine type A quiver varieties. But for the affine type A case, the corresponding algebra here is the quantum toroidal algebra. But we don't know whether there's an isomorphism between them. So the goal here today is to construct this quantum difference equation purely on the algebraic side. Yeah. Yeah, so this a really long introduction, and unfortunately I haven't introduced what I have done. So yeah, so any question for this sketch?
Maybe this is a random question. So here you define this what you call JW plus from the difference equation on the Kähler variables. But do they satisfy some equation on the equivariant variables?
Oh, that's a good question.
Yeah. Sorry, I said the other way around. You define it using equivariant variables. What about its difference equation on the Kähler variable?
On the Kähler variable, it is written as this Walker's equation. On the equivariant variable, yeah, I don't know. Yeah, I don't know which equation it satisfies. Yeah, but it's actually that it's in the general case it is a rational function over the equivariant variable, but I don't know which equation it satisfies. Yeah, yeah, I never thought about that. Yes, sorry. Yeah.
I thought that that work of Bote and Davison, they prove some kind of isomorphism with this algebras with some kind of Borchardt-Katz-Moody type of things that
Yeah, but that's only suitable for the Yangian case or for the
no,
only
I
for the
thought if
cohomology
it
case.
works for Yang, it's kind of automatically true for quantum affine. I thought. It's just
The thing that I've talked to both, but it seems that they still don't know how to proceed this proof to the fine case. Yeah, to the quantum fine case. Yeah.
okay.
Yeah.
Yeah, but somehow, yeah, okay.
Yeah. I expected that there should be some proof, but yeah, so far I don't know. Yeah.
Okay.
Yeah. So I still have 5 minutes for the break, and so I first introduced the quantum toroidal algebra, and yeah, uh, this is something that so the quantum toroidal algebra it is an algebra over the function of a qt with the following variable. And these are the currents that I just take into the package because it's really it's, it's really annoying to write it all down. Yeah. But the following definition of the currents. Or this, yeah. And this variable satisfy the following relations. So I just write down a few of this relation is written here. And this relation here. Yes, I just still writing here. Yeah. This is IG. This means that if we take all of the sign as the minus, this we should replace this ij to ji. I'll introduce this function later. Yeah. Yeah, and this zeta function is defined as the following. So it's like function of here. Yeah, and this bracket is the quantum, that means the quantum number bracket. Yeah, and plus some set relation. Yeah. And usually I prefer to write it as just UQT and as the following triangular decomposition. The positive, the neutral, the negative ones. The positive ones just stands for the positive E pi plus current. It stands for the E plus minus current, and this stands for the E minus current. Yeah. With the standard coproduct, with the Drinfeld coproduct. Yeah. I just wrote one of them. Yeah. Yeah, so the thing here is that, okay, this is like some of the candidate for the ML quantifying algebra. And the good thing here is that, but the thing here is that we need to have some candidate for the, yeah, should I write here? Which I need a candidate for the walls of algebra. UQGW. So the candidate for what's algebra, we're going to see that it is actually a slope subalgebra. But to introduce the slope subalgebra, we need to introduce a technique which is the shuffle algebra technique. Yeah, so maybe we should take a 5 minutes break or not.
I'm always for a break, so never miss a chance to take a break. How about a 5-minute break?
Yeah.
Get some water. I think 5 minutes have passed. 6 minutes.
Yeah. So I shall proceed. And
Yeah, everybody.
yes. Yeah. So the tool that we're going to take to define the slopes of algebra or to get some candidates for the words of algebra is to use the shuffle algebra techniques. So yeah. So first write down how to construct the shuffle algebra in our case. So the first thing that we need to construct a really huge vector space. This is defined as it's defined as following. It is the direct sum of the space of the colored symmetric rational functions with respect to this color. So I explain the notation here. So this is the space of the colored symmetric, which means that the color is this variable I. So this is 1, 2, 3, 4, 5. This I, it stands for the color. And for each I, there is a number. There is a positive or the non-negative number, which is like ki. So there are ki variables in the color I. And color symmetric means that the variables from zi1 to ziki, they are symmetric. So this space is really huge space constructed by this direct sum of all of these color symmetric rational functions. And on this space, it has the product structure. And this product is defined as the shuffle product. It's defined over here. Yeah. So if I give two color-symmetric rational functions, the definition is given by we take a symmetrization of the following thing. So this is still the product from these variables to the product of these variables. So you can see that the shuffle product just make the variable much more than before. And this is the symmetrization of these two, but we have to add some twisted. It is twisted by the zeta functions over here. And this zeta function is just defined. It's just defined as the zeta function in the a quantum toroidal algebra. And yeah, over this space we usually take a sub algebra. We take the sub algebra as S plus star. The algebra generated by Zi1d with this I from 1 to n and this d plus the arbitrary integers. Yeah. And in this way, actually, we could take a theorem. Yeah. This is a theorem proved by Nakajima that there exists an isomorphism, an algebra isomorphism from this S plus triple algebra with the positive part of the quantum toroidal algebra, such that it sends each of this variable to this ERD plus. Yeah. So actually, there's a really, actually can be taken as an exercise that it's like an exercise that you take like, for example, like some function, like some generating function over fi over I1d to xd. You take this function and take it as an element in the shuffle algebra and prove that it satisfies the corresponding relation in the quantum toroidal algebra. Yeah, so actually this can be thought of as an exam in this week that I promised last week. But actually this is not that hard. You can just do it's not that hard, it's not that easy. You can just do the computation just by this definition, and you see that this is really straightforward. Yeah, the hard thing here is to prove this isomorphism actually. And so actually you can just prove this kind of thing just by hand. Yeah. And here we have this fact, like the positive part of the quantum toroidal algebra is isomorphic to this S plus. So the construction of the whole algebra is in the following way. So we can take S non-negative S as the product of S plus times the positive currents. Yeah. C is bigger than 0. With the relation that has been defined in the quantum toroidal algebra once. And similarly, you could take the S non-positive as the S opposite algebra. This opposite means that we take the opposite twist of the zeta function. Yeah. And quotient by the relation. Yeah. So we define the whole shuffle algebra as the S times S minus with respect to some relation like defined by the dream field pairing. Yeah, and yeah, so you can see that from this definition, this S is just isomorphic to the original quantum toroidal algebra. Yeah, and there are some other things that maybe I need to mention that's really useful in the computation. So for example, if I take this S plus, it is a bigraded algebra. I shouldn't say it's a bigraded because there are lots of variables, and one of the gradation is given by the number of the variables. Say it's the colored variables. Yeah. And another thing is given by the homogeneous degree of the rational functions. So it's given by d, which is actually an integer. We can write it as S plus S in the following decomposition. Yeah, so this space is, so each of these subspace is a space with this number of the color variables and the homogeneous degree of degree d. Yeah. So similarly, you can define the degradation in the S minus. Sorry, this is S minus. Yeah. But it's the same. But we usually take the degree in the number of the color variables as the minus ones. Yeah, to distinguish from the positive ones. Yeah. So with this kind of stuff, now we can have some candidate for the wasabi algebra. So there's one difference, that the wasabi algebra is actually defined by the wall in the rational Picard group. So here, the candidate is by the algebra, which is instead not the wall on the in the rational Picard group, but it's given by the point in the rational Picard group. So how to define the slopes of the algebra? It is defined the following way. So we fix this rational number as in here. Yeah. And we say that we define a subspace such that all of the function is of the slope n. It actually means the following thing, that we have a function, we have a rational function such that it has the color variables, and we just take some of the color variables here. We take some of the color variables by some scaling. For example, we take the scaling from, in this notation, we take the scaling from the variable of ai plus 1 to ai plus bi. Yeah. And yeah, so this means that I take the scaling of the variables. For example, in the color I just take the variables from ai plus 1 to ai plus bi to take a scaling as goes to chi, and I divide it by the Berlin vector, and also take this chi to be on to infinity, and this AB is defined as ai, sorry, is ai bi minus ai bi minus 1 minus ai minus 1 bi. Yeah. So the slope n function means that if we take the scaling of the function in this way by chi, and we take this chi to infinity, this function should exist. And this exists for arbitrary a and b. So it's just a place in here. So this kind of the condition is like we take the degree bounding of each variable in this function, and using this kind of effect, we define the positive part of the quantum of the slope of the algebra. Of slope n. We take this slope of the algebra. It is defined as a vector space. We can define it as in the following way. So we take the slope m function space, then intersect it with each of the graded space. And actually, there's a requirement of this gradation is that we need to make sure that the vector m, the inner product of vector m with the number of variables should be equal to d, which means that actually it should be the integer. Yeah. And this is the positive part. So the negative part is the same. Yeah. We can use the same definition. And similarly, we can define the non-negative ones as the tensor product of the positive ones plus with the f, sorry. Of 5, 0. Yeah, and similarly for the non-negative ones, it should be like minus with minus. Yeah. And in this way, we use the Greenfield double still define the whole slope subalgebra. Yeah. So the good thing here is that because one thing here is that you can check the following thing, that this intersection is actually a finite dimensional vector space. So it means that actually for each of the grading, the generators or the elements in each of the gradients in the slope subalgebra is actually finite, and this is really good. Yeah, and a good result for this slope subalgebra is that is thereby negative that this is actually a subalgebra. It has an algebra structure. So it is actually well defined. Yeah. And another thing is that we could decompose the whole quantum toroidal algebra, which is isomorphic to S, into the ordered product of this slopes of the algebra. Yeah. And here, this M is arbitrary. And the theta is some totally positive vector. Yeah.
It's something like this somehow. Is that really specific to affine type A, or is there some similar
Yeah.
factorization
Exactly.
of
Exactly. In this case, each of these slopes of the algebra is actually isomorphic to the product of the quantum affine type A algebra. Yeah.
No, I mean something simpler. I think if I take some, for any quiver, one have a shuffle algebra. For any quiver, one can consider the subalgebra, and that will always factor into this tensor product like so. Is that something specific to type A? So yeah, affine type A.
Actually, for the affine type ADE and the finite type ADE, that this kind of the slopes of the algebra is isomorphic to for example, like the affine affine GLN or a SON, this kind of thing. So in principle, that they can be further factorized into this. But
no,
so if I take,
yeah, what I'm trying to ask is that the fact that this whole thing factors into the tensor product of slope subalgebras, is that a general fact or is this something specific to? I thought it's a general fact, but is that maybe you could.
For this factorization, it is a general fact. Yeah.
Yeah. Yeah. Then of course, how to identify the pieces. Maybe it's a separate question. But the fact that your S, S is some sort of, S is some kind of subalgebra in the shuffle algebra that factors into a tensor product of slope pieces. That I believe is general.
This is actually very general. It can be for arbitrary quiver, it is true, and it actually can be extended from the case of it can be extended to the case that is not in the quiver. Yeah.
Mm-hmm.
Yeah, this is widely true. Yeah.
Okay.
Yeah.
Sorry, which part of the shuffle algebra depends on the quiver? Is it like this zeta relations or?
Mm-hmm.
There are two things actually. The first is that So the first thing is that there's this twisted function, this zeta function. Actually, it depends on the quiver. So in the affine type A, we define some kind of the zeta function. Yeah. But for the other types of quiver, this twisted zeta function is really different. It's a little bit different. Yeah.
Thank you.
And the second is and from this side, actually, you can see the shuffle algebra actually depends on the quiver. Yeah. And maybe a second thing is for the slope type algebra is so the slope type algebra is this kind of thing. This inner product of A and B, because this kind of this should be 2. Yeah. Because this kind of product is like the inner product of two vector space with the insertion of the Cartan matrix. So if you take some other types of the quiver, the Cartan matrix is different. So this definition would be different. Yeah. And so shall I continue?
Mm-hmm.
Oh yeah, thank you.
So actually, for the affine type A case, that this slope algebra has the has this kind of isomorphism, which is can decompose into the product of the quantum affine GLN. And I'm not gonna say how to correspond this and this G and LH, but there's some examples that you can think about. So for example, if I take M to be the integer vector, then this Bm is isomorphic to this GLN. It's just isomorphic to the GLN. And if we take this M to be like AB, 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 yeah, then this Bm is isomorphic to the tensor product of the same quantum affine algebra, but with this kind of product. And actually, this product I just want to say that this actually the component of each of this algebra is actually commutative with each other. I mean, commutative with different components. And so using this kind of thing, you can see that if you want to write down, for example, if you want to write down the universal R matrix for the Sheffield algebra, you can just write it as the product of the universal R matrix for the slopes of the algebra. And each of these slopes of the algebra, you can have this kind of formula. It is given by the KT factorization. Yeah. So yeah. So these are some basic things about the slopes of algebra. Actually, you can find that this is really a good candidate for constructing the quantum difference operator. So now let us proceed to the construction of the.
So this type of factorization, they sort of also kind of follow what you have a tensor product, right? Because these algebras are always any kind of shuffle algebra is always what's the word? It's how to say it's one of this it's one of those Hopf algebras that the R matrix is like, it's like a canonical. So R tensor R, there's like a canonical element which is kind of a summer with basis, abscess, and dual. And so then if you have this kind of tensor product, then this means you have like a Poincare-Birkhoff basis and a dual basis somehow. Anytime you have that, and then the R matrix is the factors. That's Kharoshkin Tolstoy's argument, more or less, right?
Yeah, exactly. Yeah, and so now we have this slopes of the algebra things. Now on each of these slopes of the algebra, we can construct the quantum difference operators. So to construct the quantum difference operators, the first thing we need to do is to construct the monodromy operators. So for each of the slopes of the algebra, you can still define the work KZ equation. It is defined in the following way. And the person is that if you use the KT factorization of the universal R matrix here, actually you can just write down the solution for this equation. You can see that but the solution is really dirty. So I won't write down the solution here, but only go through the procedure, and you'll see that actually eventually you could have a really good expression. I mean for the arbitrary ones, actually the formula will be really dirty, but in our case, actually it can be really beautiful. And still use the same procedure as above. and then define still saying the monodromy operators. Yeah, this belongs to here. Oh, sorry. And actually, because the good thing that I can mention now, so if we let it act on, for example, on one of the quiver varieties, actually this difference operator, this monodromy operator will give an automorphism of each weight place. I mean, for the K theory of the quiver varieties to itself. So in this case, actually, this VW just corresponds to this VW. Yeah. And still we have the same procedure that we take some of the S and some of another point S minus L here. Like some path here. And because for now, actually, you can see the intersection of this path with something, that something is not the wall. For now, it's just a point. Like M1, M2, M3, M4, M5, M6, those kind of points here. So if we fix the quiver variety, and we can still using this procedure to define the quantum difference operator as in the following way. But for now, it is the product of the monodromy operators with respect to each of the slopes of the algebra. And the good thing here is that if we fix the quiver variety, actually, the path from S to minus L, this kind of thing here, the point that's the slope points, such that Bm is non-trivial. It's finite. Yeah. So at the first step, we can see that this product is well defined. And so now using this kind of thing, we define the difference operator this way. As the procedure above. Yeah. So here's the theorem that is the Nedrick version. Yeah. That's this operators, if I fix the quiver variety and the slope point, actually we should take the slope point to be, but not, it's not necessary to take it generic. Yeah. Then each of this is 0, and the construction of this quantum difference operator, it is independent of choice of the path from S to S minus L. Yeah. So this is like the first result for the, I think the last year's result. Yeah. And yeah, I still have some time. So I can give a sketch about this proof. The proof actually depends on two things. The first thing is that if we fix the element in the pickup group, we could take it as some kind of integers here. Sketch of the proof. So we first need to prove some kind of like a translation formula for the monodromy operators. So this is like L times. Yeah. And so in the case of the theoretic stable envelope, this proof is really easy. But in the case of the affine type A, the proof is in the case of the affine type A, I use the techniques in the fixed point basis to prove this fact. Yeah, and the second step is to define a new coproduct on the quantum toroidal algebra. And this new coproduct is defined by twisting the original Greenfield coproduct by this bunch of product of the R matrix, of the small R matrix of the slope stable algebra. And actually, there's one thing I forgot to mention that I take this as n. Yeah, this is the coproduct on the slope stable algebra, and this coproduct is defined by the standard coproduct by restricting to the homogeneous degree of the components. So the thing here is that the second step is to prove that this bigger coproduct indexed by n, if we restrict it to the slope stable algebra, it is the same as the coproduct that is originally defined on the slope stable algebra. Yeah. And the third step is we define so this is for the thing. We define the QKZ operator. I should take it as RS. Yeah. Yeah. So this is the R matrix of the. Sorry, maybe I should take it as. Yeah. Maybe that's much easier for the explanation. Yeah. So this is the R matrix corresponding to this coproduct. And if you think about this R matrix, you can think about it as the R matrix just in the case of the geometric R matrix. And you can still define this kind of R matrix and prove that this operator it commutes with the coproduct of the to prove this fact. Yeah. And combined with these three steps, actually, you can just finish the proof. Yeah. So these are the sketch of the how you prove the holomicity of this P difference operators and the independence of the path. Yeah. And there's actually one remark that this construction. But now that this construct can be generalized to arbitrary quiver, we can use the same thing to prove this fact. Yeah. And yeah, so for now, this construction is actually it can be really generous, but yeah. So here is the one question. So what is special for the affine subgroup? Why do I only tell the story about the affine type A? So the thing here is the following, that if we consider for the affine type A case, we have the following kind of a thing, that if we choose the path for example, from S to S minus L, because the choice of the path is really generic, so we can choose some generic path such that it intersects with some points. So yeah. And recall that actually, because one thing is that the solution to the ABR equation, or to the Wakese equation, this is actually called the fusion operator. The general formula is really dirty. Yeah. Not good. Yeah. So it means that the monodromy operator actually in this case is not good. It's not good neither. So if we take, but the thing here is that if we fix the quiver variety, and also we fix the, and also we take the generic path, in this case, the monodromy operators on this path can be expressed in the really closed way. Which means actually it's the filling thing, that's theorem. You can see this theorem maybe an hour later. And so if you take the
I thought it's like it's like 48 minutes or something like that.
Yeah. Yeah, and so on the generic path from S to S minus L. And this quantum difference operator, it can be written as in two ways. So the first way is like the Euclid SO2 type. In this case, the difference operator is written as the following. So I shall write it in a more feasible way. Yeah. Yeah, I shall write it here. I explain all of these notations later. Yeah. And the second is written as the EQJ1 type. This is in. Actually, the true formula for this is actually it has some coefficients like in the Q, this kind of thing, but I don't want to write it down now. But yeah, you can just get a feeling about what this formula would be like. Yeah. So here the thing is that how to express the formula like in here. So the formula here is like, so for example, if I just take the E gamma. So what is the formula for the E gamma? The E gamma formula is like filling. So if we fix the, maybe I shall not write down the formula here. So just explain the basic philosophy, the philosophy of the proof. Yeah, so this formula just says that, okay, we have some really close formula for expressing this quantum difference operator, but the philosophy into this formula is the following that. So how to interpret the slope points with the wall. So it's like the feeling that each of the slope points, you can think about it as, so each of the Bn, the slope algebra, you can think about it as, actually right, as equal to the wall algebra. It is generated by the wall algebra such that the wall corresponding to this wall algebra contains the point. Yeah. So if I write down in, so for example, if I write down in some graph, it's like, if I have this kind of walls on the plane or in the Kähler variable space. Yeah, so this is some random walls actually, yeah. So if I take the slope points over here, so you can see that on this point, it is the intersection of three walls of this one, and this one. Yeah. And first, so for example, if I take the points over here, so on this point, actually, it's like it is just the intersection of just one wall. Yeah. So the basic philosophy is fulfilling that this slope subalgebra is actually looks like it really looks like an algebra generated by the wall subalgebra, and the wall subalgebra in this case. So in this case, it's like the filling ones. So if I take, for example, like if I take one of the slope points and another slope point s minus L, if I choose the generic path, it's like, so for example, let's suppose that we take some bad path. Yeah. So on this path, you can see that we have let the path be intersected with this point which actually on this point has two walls, and this point which actually has two walls, and this point has two walls, this kind of point. So that's actually, in this case, you can see that this is not a good path, because if you try to compute it by the wall conditioning homological equation, you can see that this path, the fusion operator or the monodromy operator, is really hard to express in the closed way. But the thing is that you can choose the path that is really generic. So you can choose the path like here. So if you choose this kind of path, you have this point and this one wall. Yeah.
So
this
generic
is like
just means it just goes through. Generic just means it goes through. Doesn't go through any intersections of codimension more than one.
Yeah.
And then
it just goes through the codimensional one thing.
Those things are just kind of roots of your algebra, right? And so you're saying that the roots, all roots of all roots are either
exactly
either real roots or
isotropic
roots,
right? Either real roots or the imaginary roots. Yeah, exactly. Yeah. So in this case, it's like, so because for the case of the quantum toroidal ones, you can actually have just two kinds of roots. One is the real roots, and one is the imaginary roots. So in this case, this real root just corresponds to the UPSR2, and this imaginary root just corresponds to the GL1. Yeah. And so these are the basic philosophy. And the elements here and here, the elements actually look like the filling. So these kind of elements. Looks like the filling. So I should give one complicated formula, just give you a feeling about what this formula should be like. Yeah. It should be like the filling. So it's like, this is like a product of L from I to J minus 1 I. Sorry, this is I plus 1, J minus 1, J. I think I write it into the wrong way, but the order should be opposite. Yeah, but no, that's not a big deal. Yeah. So the formula, it looks like the filling. So this E, F, and alpha, it looks like this kind of formula. Yeah. So it means that if you want to do the real computation, actually, you can, if you're really genius in doing the computation of this kind of thing, you can just put all the fixed point spaces into this kind of formula and do the computation. Yeah, so to some sense, it just reduces the computation. Yeah. And this theorem actually has a really some good consequence of this theorem. The good consequence is on the filling that cohomological limit of the difference equation of this quantum difference operator So if we do the cohomological limit, it's like filling. So we take the so this equation is like we take PLZ because S there Z psi Z. Yeah, and we take the limit as take this QTP to goes to 1 with the fact that sorry, I should take this way. I should take Q equals kappa h bar 1 h bar 2 and T equals E kappa h bar 1 h bar 2 and let this P goes to like E kappa. Yeah. So I take the limit as this kappa goes to 1, and which means that this QP T goes to 1. Yeah. And in this case, because this formula is actually living on the K theory, so under this limit, it just goes to the cohomological case. Yeah. So yeah, it means that actually on this limit, this difference equation will go to from like a difference equation to some differential equation. Yeah, and the theorem here is that the cohomological limit of the difference operator is equal to the quantum multiplication operator of this line bundle here in the quantum cohomology. Of the quiver variety, which is written in the following way. Yeah, here is like Z, I, J. Oh, sorry, I should take it as alpha. Alpha are the roots, are the positive roots in the SLN Lie algebra. Yes, absolutely. And these are like E alpha, E minus alpha. Yeah, plus some of the scaling operators. Yeah. So one of the good results for this kind of the reduction of the computation is that if we do the cohomological limit of the quantum difference operator or the quantum difference equation, the cohomological limit is actually equivalent to the Dubrovin connection of the quiver varieties up to a scaling operator. Yeah. So this result actually can lead to another fact that the monodromy representation, you can just do the analysis of the quantum difference equation of this monodromy matrix and using this monodromy matrix and the cohomological limit to analyze the monodromy representation of the Dubrovin connection. So the final result is that the monodromy representation for the Dubrovin connection, like here, yeah. It's like I take like this some singular walls to the end of to the automorphism of is generated by this monodromy operators, and here is actually the monodromy operators in some limit of the original monodromy operators, but eventually can be written as this. Yeah. So this is the universal R matrix of the slope step algebra. and it belongs to this closed algebra by replacing the variable in this way. So we should replace this q to be like e h bar 1 h bar 2, and q like e h bar 1 minus h bar 2. Yeah. So in this way, actually, you could use because this kind of the monodromy operator is really computable, because if we choose the generic n, this Rn, it has only two forms. One is of the UQSO2 universal R matrix. Another is just the quantum Heisenberg universal R matrix. Yeah. So in this actually, it can be computable for it is useful for us to compute the monodromy representation for the Dubrovin connection. But the thing here is that it's actually that because we still cannot figure out how to use this formula to figure out the relation between these monodromy operators. Yeah. So actually there are some, actually these are all what I want to talk about today. Yeah. So that's the end of my talk. Yeah.
Right. How do we? All right. Questions?
Can you say a little bit more about how the quantum difference operators degenerate the Dubrovin connection? So like, where do the higher powers of these E and F gammas go?
Yeah, this is because of filling. So this degeneration is like a filling so these are the formulas for the monodromy operators. And you can see that if you take, so this kind of the construction is like if you have the difference operator here, and you can write it as 1 plus some like E1 kappa plus 2 kappa squared, this kind of thing. Yeah, and this kind of thing is actually, and this resting term of the kappa, which has the order higher or equal to 2, actually it will not appear in the degenerate limit because we need to take the kappa to be 0. And we take the derivative of this ML with respect to this kappa. So in the formula, for example, like here and here, actually this formula is not obvious, but if you take the formula of the UQSO2, this Q minus Q1 is like E, for example, I take a E H kappa, E minus kappa, it's like 2 sines H bar kappa. So if you take the term, if you take the higher term, like this n goes to 2, actually, you take the kappa to be 0, this term can only be left with the kappa which has the order equal to or higher than 2. Yeah. So that's the key of the computation. Yeah. So it means actually you can have only the linear term left. Yeah. Others. Yeah.
Suppose I have some general, suppose I have a general, some kind of Q difference equation. Then of course I can always take a limit to the differential equation. But what sort of thing do I need to, like if I want to somehow express the monodromy of this differential equation in terms of the original Q difference equation, what sort of thing do I need? What sort of structure do I need to
You mean how to obtain the monodromy from the difference equation?
No, this I understand how this works in this example, but in general, what sort of structure is there? Suppose is there some sort of like what kind of structure is there some reasonable name to the structure that if I have a Q difference equation, I can somehow not just get a differential equation out of it, but also differential equation together with the computation of the monodromy? Is that can be said? Something like that.
The only thing I know is that because the computation here is the only thing I know is that if I have the difference equation, I have the degenerate limit to the differential equation. Usually the thing is that they have this is really general, that they have the connection matrix or the monodromy matrix for this difference equation, and we take the difference, we take this p here to goes to 1, and in this way, this monodromy matrix or the connection matrix will give the monodromy representation for the corresponding differential equation. But the thing here, this is like some kind of like the general procedure, but that procedure is like you can't take too much of the, you can't know what kind of idea, which kind of the ingredients that you have in this connection matrix or the monodromy matrix. Yeah, the key thing here is that because this monodromy matrix, it is like infinite product of this monodromy operators. So we can and actually you can compute two kinds of the limits for this monodromy.
This is the complications here somehow have to do with, you have a kind of, somehow many walls and many dimensional space. But suppose my space is one dimensional, just have some kind of walls, let's say all rational numbers or something like that. And then I'm asking, then this sort of kind of path independence, that's just a vacuous condition. It's just, you just have my difference equation, just a product of matrices along a path, right?
Yeah.
And so then is that what sort of condition guarantees that I can, if I take a differential limit of that connection, that I can also control its monodromy?
I think maybe maybe actually there's not too much constraint for the definition of this Wöhler matrix. Yeah. Sorry, of this monodromy operators. Yeah. Of these walls.
Yeah, I don't know.
Yeah, but yeah.
I wonder. So anyhow, you don't have to answer this question now, but I thought it's kind of an interesting question. Well, I don't know. Even you.
I think actually it's really general that we can take. Yeah, I think it's really general because in this competition, actually, I don't need too much about it.
Yeah, like what if branch cuts form or something like this?
Yeah, somehow that I doubt. Yeah. Maybe.
Oh yeah, that doesn't work.
If it's, so to speak, yeah, I don't know, because it's basically, the solution of Q-difference equation in one variable is just, just an infinite product of matrices. That's all.
Yeah.
And then you wanna somehow say something about, I'm not sure what. So okay, maybe I should stop asking open-ended questions on the account of the fact that we need to. Like, I simply need more than 26 minutes to get to the pizza place. So maybe I'd better start right now. Other questions? Well, if not, then let's thank Tianqing for again, and then that concludes the seminar for this semester. Thanks everybody. That was fun. Yeah. See you soon in the pizza place. Okay.
See you.
Uh-huh.